Welcome back everyone. In today's video, we will solve some GATE previous year questions on vector subspaces and dimension of vector subspaces. We will see how we can apply the concept which we learned in the previous video while solving these questions. Also, if my videos are helping you, then please like my video, subscribe my channel, and also share with others. This highly motivates me to create such content. So let's start. This is the first question on your screen. Which of the following are subspace of Mn R where Mn is n cross n matrix? So I would recommend that you pause this video and try to solve this question by your own. Okay, so let's first see what is this. This is Mn R. So what this representation means, here Mn is a n cross n matrix, all right, and elements of Mn, that is the matrix belonging to this vector space, elements of Mn belongs to R, that is these are real values. These matrix doesn't contain any complex value. So they are asking that is any one of these is a subspace or not. So it is a multiple choice question, so one or more than one could be a valid subspace. So we will begin one by one. We will first see the first scenario, the first set. It says that set of all matrix A belonging to the vector space MNR. So MNR is a vector space. We already know that the set of all n by n matrix is a vector space, right? So Mn is a vector space. This we already seen in our lectures. That is set of all possible n by n matrices. So this is a valid vector space. So now we need to check whether these four options are a vector subspace of this vector space Mn. So the first one is this. It says the set of all vectors A belonging to the vector space Mn such that the determinant of those matrices is 0. So if you remember, I have told you that there are two things we need to check if a space given is a valid vector subspace or not. The first thing is that the zero vector should belong to the subspace, right? And the second one is linear combination, that is alpha v plus beta w should be in the subspace given that v and w belong to subspace. So basically the second point says that if we have two vectors v and w which already belong to that subspace, then their linear combination should also belong to that subspace, right? So this is a, let us suppose this is a subspace. If v and w belong to that subspace, then their linear combination v plus w or alpha times v plus beta times w also belong to the subspace. So we need to check these two things. So we will first check the first one. Does the zero vector belong to the subspace or not? I have already told you that this is a matrix space. So here the zero vector is a matrix of all zero. So we can write it as what is the zero vector in our case? It is basically a matrix n cross n, a n cross n of all zeros, That is 0 0 0 0 0 0. Yeah, this belongs to this subspace. Why? Because the determinant of A is 0. The matrix containing all 0, the determinant of such a matrix is 0. So we can say that 0 vector belong to this subspace. Now we will see this second condition is valid or not. So let us suppose we take two matrices A1 such that A1 and A2 such that they belong to Mn. So this is one matrix, all right, and this is another matrix A2. So we will take two matrices such that they belong to this set, not Mn, sorry, I said that by mistake, to this set. So these two matrices A1 and A2 belong to this set? Yes, it belongs to the set because the determinant of A1 is 0 and determinant of A2 is 0. Okay, so make sure for the second condition, whatever V and W you are taking, they should first be in the subspace. If they are itself not in the subspace, then you cannot say that okay, their linear combination should be in subspace. If V and W are in the subspace, then their linear combination should be in subspace also. So we have seen that A1 and A2, A1 belong to this set, that is set of all matrices whose determinant is 0, and A2 also belong to that set because the determinant is 0. But let us suppose we take a linear combination of it. So we take A1 plus A2. This is a valid linear combination, and if we multiply, we get this matrix, right? And its determinant is, the determinant of A1 plus A2 is 1, which is not 0. So therefore we can say that A1 and A2 belongs to the vector space. Let us suppose we name this vector space W. Okay. Let us suppose we name this vector space W for simplicity. W1, the first one, W1. Alright, so we can say A1 and A2 belongs to the space W1, but their linear combination A1 plus A2 doesn't belong to W2. So the second condition is failed. Okay, so therefore we can say that therefore W1 is not a subspace. Alright, so W1 is not a subspace of Mn. Alright, now let us see the second subspace. The second subspace is W2 equals to A belonging to MNR such that the trace of the matrix is 0. So by the way, what is the trace? Trace is nothing but uh, the sum of the diagonal elements. Okay, the trace of A is sum of diagonal elements. All right. So first of all, the first thing is W2 contains null matrix, right? It contains the null matrix, that is 0 vector. So the first condition is already satisfied. The first condition is already satisfied. That is W2 contain the null matrix. So W2 contains the null matrix. So the first thing is satisfied, right? Now we will check the second one. So again we will take two matrices A1. So for example, A1 is such that its trace is 0. So let us suppose whatever element I take here, A B, I take let us suppose I take minus C and plus C here, right? So the trace of A1 is 0, that is sum of the diagonal element is 0. Let us suppose I take another matrix such that this is minus alpha and this is alpha and this is C and D, something like that. Okay, so the trace of A2 is also 0, right? So we can say that both A1 and A2 belongs to W2. This is fine. Now let's check A1 plus A2. So if we check A1 plus A2, we can say we will get this minus C minus alpha, uh, A plus C, B plus D, and this is C plus alpha. If you now check the trace, of A1 plus A2, it is 0. Okay, so you take any combination, so we can say that A1 plus A2 also belongs to W2. You take any combination alpha times A1 uh, plus or I would say you take any combination uh, n times A1 plus m times A2, any linear combination, it will always belong to the subspace W2. You can prove that out, like, because because we are simply adding there these elements, right? if the sum of these two elements is 0, the sum of these two elements is 0, then the sum of all the four elements is also going to be 0. So we can say that if a1 a2 belongs to w2, then any linear combination of a1 a2 also belong to w2. Therefore both the properties are satisfied, so we can say that w2 is a valid subspace, of MNR. All right, now let's see the third one. We will see the third one, that is W3. W3 is the set of matrix A belonging to MNR such that the rank of the matrix A is 1. Now this is pretty simple. You don't even need to check this second property. Why? Because the first property itself is failing, that is zero vector, that is the null vector doesn't belong. So the null vector, or in this case the null matrix, that is the null matrix doesn't belong to W3. Why? Because the rank of null matrix is 0. So the rank of null matrix is 0, but this set is set of all matrices such that their rank is 1. If that is the case, then null matrix cannot belong to W3, right? So we can say that null matrix or the null element doesn't belongs to W3. Therefore, W3 is not a subspace. All right. And D is pretty simple. We have seen this in video that the symmetric matrices, the set of symmetric matrix is a subspace. So D, that is W4, that is set of symmetric matrices is a subspace. All right. So we have seen all the four subspaces. Okay, let's see the next question. So this is an interesting question. This is pretty important. So we are given this set. It is saying consider the set V of vector xyz belonging to R cube such that alpha times x plus beta times y plus z equal to gamma, where alpha, beta, gamma are real values. So it is saying for which of the following choices A, B, C, D, option A, B, C, D, the set V become a 2D subspace. So it become a 2D space. So what should be the values of alpha, beta, gamma such that this set V become a valid 2D subspace of R3 over R. It is saying R3 over R. Over R basically means that the elements belonging to this set V takes only real value. They cannot take complex values. Okay. So if we see the first option, it says that alpha 0, beta 1, gamma 0. So if we put alpha, beta, gamma here, so 0, 1, 0. So this becomes this particular equation will simply become y plus z equal to 0. Okay, so first of all, I will tell you two things that there to solve this question, there are two approaches. One is the graphical way. You can visualize these equations and you can tell, okay, is it a valid subspace or not? And second is a mathematical way. All right. So if you remember, if you have seen our video on all the subspaces of R cube, you can check out this video. I think it is. This video column subspace, sorry, it is a video of vector subspaces. In that video I have explained all the valid subspaces of R cube. So one of the valid subspace of R cube is a plane passing through origin, is a plane passing through origin, passing through origin. ठीक है, a plane passing through origin is a valid subspace. All right, so a plane passing through origin is a subspace of R cube. All right. So all we need to check in this equation is this a plane, and if it is the case, is it passing through the origin? The first of all, first thing is that it is a plane. I mean, it's a equation, right? For y plus z containing two variable y and z. So it's a valid plane. These y and z are the y plus z equal to 0 is a plane. But does it pass through origin? Let's see. So because this we are talking about r cube, so origin is 0 comma 0 comma 0. So let's put this coordinate in this equation. So we get 0 plus 0 and equal to 0. So 0 equal to 0. Yeah, this origin 0 0 0 belong to y plus z. So we can say that 0 vector belong to this plane y plus z equal to 0. So this is nothing. This is this is a plane in R cube passing through origin, passing through origin, right? And we know that to prove a space is a valid subspace or not, we need to prove these 2 points. The first one is already proved, that the origin in R cube, zero vector is the origin itself, right? So we have seen that the zero vector, that is the null vector, is belonging to this particular space. So the first condition is valid. Second condition we have seen from the first video of linear algebra itself, that if we take any two vector in a plane, if you take any two vector in a plane, their linear combination always stays in the plane. So I don't want to prove that again and again. All right. So this is a valid subspace because null vector belong to this subspace, and also you take any two vector in this subspace, the linear combination belong to it. And you don't even need to think all these things, because I have already shown in a video that a plane passing through origin is a subspace. So you just need to check whether this plane is passing through origin or not. This is the graphical way of solving this question. Now the other way is, for example, it is this is the vectors, right? X, Y, Z. This is the vector X, Y, Z belonging to R cube, and this is the constraint. This is the constraint, right? So I need to check this y plus z equal to 0. So I will apply some row operation to get this y plus z equation, right? So I will do R2 uh, goes to R2 plus R3, right? So uh, this becomes x, the y plus z, and z. And now I apply the constraint. The constraint is y plus z equal to 0. So this becomes x, 0 and z. Now if I ask you a question, if I ask you a question that the set of all vectors of this type, which type, where the y component is 0, if this is the xy plane, all right, if this is the xy plane, and let us suppose this is x, this is y, this is x, this is z, all right. So the set of all vector where y component is 0 is nothing but this, is this, right? That is the xz plane. So if you take any two such vector, their linear combination is also belong to that YZ plane, right? So this is a valid subspace, valid subspace. And also origin also belong to it, because the YZ and the XZ plane contains the origin, right? What is this? This is nothing but the XZ plane. This is the XZ plane, right? And we can see that the XZ plane is a valid subspace, right? Because origin belong to the XZ plane and it is a plane, so the linear combination stays in the plane itself. All right. Now I will for the remaining three I will move fast because they are very similar. The second one is alpha 0 beta 0 alpha 0 beta 1 gamma 1. So if you put this in this equation, alpha beta gamma, then you will get this equation, y plus z equals to 1. Now is this a plane? Yeah, it is a plane. It is a plane, but the question is, does this plane contain the null vector, that is zero vector? That is, or in simple term, does this plane passes through origin? So let's check. This is the origin coordinates. So we will put it 0 plus 0 equal to 1, 0 equal to 1. So no, 0 is not equal to 1. So this plane, this plane doesn't pass through origin. Or we can also say, let us suppose, yeah, we can also say that let us suppose this is the subspace W1 and this is the subspace W2. All right. So we can also say that W2 doesn't contain the null vector. That is the first condition. This first condition itself is failed. So no need to check the linear combination. But linear combination will stay in this plane itself because it's a plane. And we know that linear combination is bounded in a plane. Yeah, so the third subspace is z equal to 0. The third configuration is alpha 0, beta 0, gamma 0. So if you put alpha, beta, gamma 0, so you get z equal to 0. So what is z equal to 0? Z equal to 0 is nothing but the xy plane. It is the xy plane, right? And it is a plane passing through origin, right? It's a xy plane, right? It is the plane passing through origin. So you can even check 0, 0, 0 passes through W3, right? So therefore W3 is a subspace. So W3 is also a subspace. Now let's check D, option D. Let's check option D. So for option D, alpha is 1, beta is 1, gamma is 0. So if you put gamma 0, alpha 1, beta 1, you get x plus y plus z equal to 0. You get x plus y plus z equal to 0. All right. So is this a valid subspace? First of all, it's a plane, right? It is a plane in R cube. We just need to check if it is passing through origin or not. So this is the origin. Let's see, 0 plus 0 plus 0 equal to 0, 0 equal to 0. Yes. So it is a plane in R cube passing through origin, right? It is a plane in R cube passing through origin. So so it is a valid subspace of R cube. So this is the first subspace y plus z equal to 0. So you can see it is passing through origin. So yeah, it is a valid subspace. This is the second one, the blue one. So you can see that this is not a valid subspace, right? See, this is a plane in R3, but it is not passing through origin. See, here is the origin. Here is the origin. You can see my cursor, but the plane is not passing through origin. So it is not a valid subspace. This is the third one, z equal to 0, that is xy plane, a valid subspace. And this is the fourth one. This is the fourth one. This is the fourth one. This is also passing through origin and is a plane, so it's a valid subspace. So let's start our last question, question 7. So we are given W1 and W2. W1 is xy, all the vector xyz, such that we are given two restrictions. We are given x plus y equal to 0 and 2x plus 2y equal to 0. Similarly, we are given W2. Here there is only one restriction. So they are asking us the dimension. What is the dimension of W1 and W2? All right. So first of all, in such question, if you need to find the dimension, so the formula, the formula is first of all, see to which dimension the vectors are belonging. So the vector is belonging to R3, right? So the dimension of R3 is 3. Then you need to subtract the number of linearly independent restriction. All right, you need to subtract the number of linearly independent restriction. So if we see, yeah, if we see W1, there are two restrictions, right? X1 plus, x plus y equal to 0 and 2x plus 2y equal to 0. But if you see, these are connected because if you take 2 common, x plus y equal to 0, then this basically means x plus y equal to 0. So these two restrictions are same. So you can say that these two restrictions are linearly dependent. So we can consider only this one. We can remove this out. So what is the dimension of W1? So the dimension of W1 is what is the dimension of this space? It is 3, right? Minus the number of linearly independent restrictions. So here there is only one linearly independent restriction. So this become 2. So this is nothing but number of linearly independent restrictions. So what I mean by restriction, basically restriction is you are putting some condition, right? You are putting some condition. If you simply remove this condition, this W1 contains all the vector XYZ. So which is the entire XYZ volume. But then you put some restriction that it should contain all the vector XYZ, but the vector should follow this particular equation, that is x plus y equal to 0. So this is a restriction. We are putting a restriction, right? Now let's check for W2. This is for W1, right? Now let's check for W2. Now if you see W2 is x plus y plus z equal to 1. Now before checking the dimension, check that it is even a valid subspace or not. So the first thing we check if origin is passing to this subspace or not, that is this subspace contain null vector or not. So we do 0 plus 0 plus 0 equal to 1. So 0 equal to 1, no. Therefore, the null vector doesn't belong to W2, hence not a subspace. All right. So in this case, the dimension of W1 is 2. So this is correct, and option D is correct.